Globally, over 100 billion garments are produced every year, and 90% of them end up in landfills. That is the equivalent of 8 truckloads of garments every minute. Only 1% can be recycled. This creates an immense strain on the planet's ecosystem. As a solution for this globally recognized issue, circular economy was introduced. How do we improve the recycling rate of pre-consumer textile waste? This is where the need of risk-based classification arises. If high-risk waste and low-risk waste recycled together, the output material will become useless. Risk-based classification can prevent difficult to recycle material from lowering the quality of recycled fiber. Since materials with different level of recyclability can be separated, this process ensures that the most valuable textiles are processed first. Also, a proper risk-based classification can help understanding which to be recycled mechanically and which to be recycled chemically. This prevents overconsumption of energy during recycling process. According to the resources, for a better recycling process, different fiber types should be recycled separately. For an example, single fiber textiles with the longer length of fiber like wool, cotton are suitable for mechanical recycling. When it comes to classification according to color of fabric, it is important to understand that dark colors like black has more chemicals added in fabric dyeing process. They may contain heavy metals and other harmful chemicals. Chemical treatments and additives are one of the main concerns when it comes to risk-based classification. During wet processes like dyeing, finishing, waterproofing and coating, lots of chemicals get added to the fabric. Azure dyes, chlorine-based bleach, halogenated fire retardants and PFAS are few hazardous chemicals in these processes. The order of classification is very important. I have decided to start the fabric classification process with classification of fiber type. Natural fiber, synthetic and blend fiber compositions will be identified. Then, color classification will take place. Light color, dark color and multicolored textile waste will be identified in this step. The amount of chemicals added to fabric during manufacturing process is quite high. Therefore, identifying most hazardous chemicals and compositions will be prioritized as the third step. This AI-powered classification model is not just theoretical. It has been proven feasible through research and experimental tests. Studies show that AI-driven textile classification can achieve 90% to 100% accuracy in identifying pure fiber and binary fiber mixtures. In this proposed AI-driven sorting system, different characteristics need to be captured with various types of technologies. According to research, NIR spectroscopy, HSI, and X-ray fluorescence spectroscopy are the most suitable method of collecting data from the textile waste. When it comes to NIR spectroscopy, research shows that it is the most suitable method to identify fiber types. This combined with CNN can correctly identify most of the pure and binary fibers, but it cannot detect full range of chemicals. HSI technology can analyze and categorize most of the chemicals and has the ability to map the distribution of chemicals within textile. Most feasible option when it comes to detecting heavy metals is X-ray fluorescence spectroscopy. This has the ability to identify various compositions of heavy metals, but it is rather expensive. While AI significantly improved textile waste sorting, certain knowledge gaps still exist. Even within the same class of chemicals, there can be significant variations in formulation. Large number of variations can be a challenge for the development of robust classification algorithm. Recyclability does not have a standardized numerical scale to assess the difficulty of recycling different fiber and blends, especially chemical recycling. This makes it difficult to compare materials and make informed decisions about the pathways. Identifying and separating in complex blends remain a challenge, especially for those contain multiple fiber types. This project is structured into key phases. Moving forward, main focus of the next few weeks would be data collection, machine learning model development. Model training system integration optimization will be done in the span of 9 weeks into the 8th sem. Final model development will ideally take 4 weeks. As transitioning towards implementation of the system, next step will be data collection for calibration and prediction purposes. Over the coming week, comprehensive data sets will be gathered.